Hi, we're going to go over quiz number 5. Okay, so for quiz number 5, you draw vectors. You draw vectors to represent an electric field, and you draw vectors to represent the force. Even though these are both vectors, they aren't representing the same thing. Let's write an equation for the electric field. The electric field is equal to Coulomb's constant times Q over R squared. This just tells me the direction, the magnitude of the electric field. You also need to know the direction of an electric field. If I have some positive charge, the direction of the electric field is always directly away from the positive charge, and the magnitude can be determined by this. If I have a negative charge, the electric field is always towards the negative charge. Again, the magnitude can be determined by this. Well, what do I mean the magnitude? The magnitude is different at different positions. Let's take a positive charge. If I'm this far away from the charge, let's say I'm at this point, the magnitude is going to be kind of strong. And the reason why is because I'm close to it. R is small because I'm close to it, which makes E larger. If I choose a point further away and say, what is the electric field? It's going to be small because R will get larger, which will make E get smaller. The electric field doesn't really mean something's happening here. I could draw a vector representing it. I drew a larger vector here and a smaller vector here. They may not be proportional. But let me also include a magnitude for this R. The magnitude tells me how long the vectors should be proportionally to each other. We need to come up with a number in order to do that. Let's say this is 2 coulombs. Let's say this distance is R equals 1 meter. That means this distance would be 2, 3, 4, 5, 6 meters away. So what I've done is I've come up with a value of Q. This is my source charge. It's the source of an electric field. I've also given you values of R. R is the distance from my source charge. So the value of the electric field here is going to be K sub E times 2 over R squared. That's just going to be 2 K sub E. The strength of my electric field here is going to be K sub E times 2 again. My source charge is still the same charge, 2 coulombs, over the distance squared, 36. So that's equal to K sub E over 18. So if I were to now redraw these vectors with correct lengths, this one would be 36 times larger or longer than this one. The fact that this one is 6 times as far away makes it significantly weaker. The electric field still points away from that point, but it's weaker since it's further away. Now, I'm drawing these electric field vectors. We can also draw electric field lines, and that's what question 1 asked for. Question 1, I had some positive charge A, and I asked you to draw electric field lines. When I draw lines, I also had it in a box, and that was to contain how long I want your lines to be. When I draw field lines, they basically go off forever. I need to draw them going away from the charge because it's a positive charge, and they go off forever. If it were negative, I would draw field lines going towards it. This is an acceptable answer, and the reason is I have field lines pointing away from the charge, and they're symmetrical. Now, of course, we're drawing this in a two-dimensional space. There's really a line coming out from the charge, a line going past in the board through the wall. I probably would add more lines to this, just because. I mean, you don't know the strength of the charge. So it really doesn't matter. And even if you did know the strength of the charge, the number of lines you draw is just proportional to other charges that might have fewer or more lines because they have less or more charge. This is another acceptable answer for this question. These again are electric field lines. If I were to determine what is the vector at different locations, I could find out what is the field vector here or what is the field vector here. Let's find the field vector right here. The field vector is going to point in the same direction as a field line, but its length is going to be dependent on that equation. The closer I am to A, the smaller R is, the larger E will be. The further I go away, the smaller my magnitude is going to be. These field lines, you can imagine, are basically not an addition, but connect the dots of the field vectors. We can somehow determine from these field lines how strong these vectors would be. When these field lines are close to other field lines, you get strong vectors. When you're further away from other field lines, your vectors are weaker. So that's our kind of intuitive approach to say how strong is a field at locations. It's related to the density or the closeness of one field line to another at some particular location. Okay, question 2. I have a box. I have a charge B in it. I tell you that there's an electric field of 82 newtons per coulomb. And I say that it's a constant electric field pointing downwards. That means everywhere in this box, there's an electric field pointing downwards. And the magnitude of that field is 82. It's everywhere in this box. Now, the part that really I'm curious about is what is the electric field at the location of B? The electric field at the location of B, I'm going to write E equals 82. We know it's newtons per coulomb. My question, though, doesn't say what's the electric field at B. My question says, what is the force on B? I tell you that B is a charge of negative 10 coulombs. Now, some of you said, oh, B must create its own electric field. It does. It creates an electric field that points in towards it. I'm just drawing some vectors, but I didn't ask for that. I don't care about that. The reason is, even though B creates an electric field, it doesn't create a force on itself with that electric field. It's only going to react to electric fields caused by other sources. So we just want to know, what is the force on charge B? We know that charge B isn't going to cause a force on itself. Even though it creates an electric field, the electric field that B causes would cause a force on maybe some other charge. But I'm not asking about a force on another charge. I want to know the force on B. We have an equation that says the force is equal to the charge times the electric field. This is the electric field caused by other sources, and this is our test charge. Well, we don't know what other sources caused this electric field, but I told you what the value of the electric field is. And so we know that E is 82, and it points downwards. I told you B has a charge of minus 10 coulombs. And so our total force is going to be negative 820 newtons, because our field is in newtons per coulomb and our charge is in coulombs. What does this negative mean? What it means is that even though the electric field is pointing downwards, the force is going to be in the opposite direction. The negative means that a negative charge feels a force in the opposite direction of the electric field. If it were a positive charge, it would feel a force in the direction of the electric field. The magnitude of this force, I drew the vector right here, is 820 newtons. I didn't put a negative here because I used the negative to draw the direction of the vector. And that means the magnitude is how long the vector is. Now, there's no reason to call the vector a negative length because we already have it drawn in the correct direction. This is the answer to number 2. Okay, so for number 3, I had a charge configuration. My charge configuration looks like this. I have a charge C and a charge D. I tell you that C is 2 coulombs, positive 2 coulombs. I tell you D is positive 3 coulombs. I tell you the distance between these charges is 2 meters. Now I have 2 other points on here. I have point I, which is a distance of 1 meter, and I have point II, which is directly between these points but another distance of 1 meter above them. My question is, What does the electric field do at, or total electric field at I, and also electric field due to the individual charges? What's the electric field at II, both due to the individual charges and the total electric field? So one issue some people had was they said, oh, I have two positive charges. They repel each other. Yeah, they repel each other. I don't care. That's not what I'm asking. If I asked you, what is the force on D, then you would say, yes, it's in that direction, and you could find out some magnitude. But I'm just curious, what is the electric field here when we have this charge configuration? So I don't care how they interact with each other at this moment. There are two electric field vectors at this point. There will be one due to the charge C and one due to charge D. And we're going to use this equation. The very first thing we did at the beginning of this video is what we're going to do now, but we're doing it at another specific point. So there's an electric field due to C, and it's going to be pretty strong. It's going to be away from C since C is positive. It's pretty strong because I'm close to it. R is a small number, which means E is large. There's also an electric field due to D. I think it's going to be weaker. Even though D is stronger, I'm much further away, and it falls off more quickly with respect to distance. R is squared than it does to charge. So it's going to be weaker. Right now, I've just general ideas of what the fields may look like, but I don't know what they are yet. I have to calculate the magnitudes, and then I can adjust these vectors to be the correct magnitude. All I know right now is the direction that the fields point. Now, I really should draw the electric field at D on top of this charge, because they originate from this point. And so I want both of my electric fields to originate from the same point, from the point of interest. Sometimes I'll just stack them on top of each other because I need to add them together anyways eventually. But let's figure out the magnitude. So the magnitude of the electric field at C, or due to C at point I, is equal to K sub E times Q, again over R squared, equals K sub E. Q is going to be our source charge. C is the source of the electric field due to C. So we'll make it 2. My distance between my source and the point of interest is 1 meter. So I'm going to say 1 meter squared. My total electric field is 2 K sub E. The units of my electric field I could put are newtons per coulomb. So my length of my E sub C vector should be about 2 times Coulomb's constant. Let's figure out what the length of my vector due to D at point I is. Again, I'm using this same equation, but I want to plug in my source charge, which is 3 coulombs. My distance is now 3 meters, so I need to do 3 meters squared. That's equal to K sub E over 3, because 3, I could divide a 3 from the top and the bottom. And the units, again, are newtons per coulomb. So my E sub C vector, if I want to redraw this, my electric field due to charge C is some length 2 times K sub E. Due to D, though, is going to be 1/6 of this value, because it's just K sub E over 3. So if I try to estimate 1/6 of that value, I could draw my electric field vector due to charge D. These are the individual electric fields due to charge C and D. Now I want to find out what is the total electric field. And to do this, I need to do vector addition. Vector addition is very simple in this case because both of these vectors are pointing in the same direction. And so I want to add together E sub C, which is 2K sub E, plus E sub D, which is K sub E over 3. So if I come up with a common denominator, I could call this 6K sub E over 3. And the total electric field is the addition of those two. It'll be 7 Coulomb's constant over 3 newtons per coulomb. So that's the answer for what is the electric field at point I due to the individual charges, and also what's the total electric field. Let's do point II right now. This point will be a little more difficult. First of all, we need to find out what is the distance to that point, so we can know what r is. It'll be easier in the sense that r will be the same for both c and d. They're both the same distance. But the electric fields will point in different directions. So when we do vector addition, we can't just add them together. We have to come up with triangles. So the electric field at this point due to C, again, I'm going to erase this just to get rid of it. Due to C is pointing away from it. Here's the electric field due to C. The electric field due to D also points away from it. What is the strength of this electric field going to be compared to this? Well, R is the same, but charge D is bigger than charge C. And so therefore, it should be 3/2 as long as the electric field due to C. These are just rough drawings of this. Let's calculate the actual magnitude of the electric fields, and then we can adjust them if necessary. First, we need to find what is this distance. So this total distance is 2 meters. This distance is about 1 meter. This distance I told you is 1 meter. That means this distance is going to be √2 meters. You could just use the Pythagorean theorem to determine what this total distance is. This distance is going to be the same as this distance. So r in both of our scenarios will be √2. The electric field due to C then, we'll use that equation, is k sub e times q, my source charge is 2, over r squared. That's √2 squared, which is just 2. And so electric field due to C is just k sub e. Our electric field at D is k sub e times 3 over, again, √2 squared, which is going to be 2, equals 3/2 k sub e. And so this is 2/2 k sub e. Let's just make it 2/2 and 3/2 so we have a common denominator. This will be 1.5 times as long as that. And I think I drew them just about right. We have enough information to answer the first part of the question, which is what is the E field due to C? It's that direction and that magnitude. What's the E field due to D? That direction and that magnitude. Now we want to find the total electric field. To find this out, we have to add the vectors together. And you can't just add these two numbers together because the vectors are not pointing in the same directions. Luckily, these two vectors, and well, first of all, in order to add them together, you have to align the vectors head to tail, head to tail. It doesn't matter what order you add them together, we'll come up with the same final vector. And so here's the electric field due to C. This is the electric field due to D. The total electric field goes from the way beginning, where I started adding, to the way end, wherever my final vector landed. And so that's E total. It's going to be up and to the left. To find the magnitude, we have to build a triangle. Sometimes we'll want to break things up into horizontal and vertical components. We could do that here, but we don't need to. The reason is we have a nice right angle right here. We can just do the Pythagorean theorem to come up with that. Let's do that real quick, and then I'll give you an idea of how I would have broken it up if they weren't at a nice right angle. So E sub C is k sub e. This is 3/2 k sub e. Pythagorean theorem says E total is going to be the square root of k sub e squared plus 3/2 k sub e, this quantity squared. We can take a k sub e out of this square root and just end up with 1 squared plus 3/2 squared. That's because there's a k sub e squared right here. There will be a k sub e squared right here. I'll take it step by step. That'd be k sub e squared times 1 plus 3/2 squared. We could just take that k sub e squared out of there. This is enough of an answer for me. You can go ahead and square this, make it 9/4, come up with a common denominator. 9/4 plus 4/4 would be 13/4. You could do that too. They look the same to me. Either way is fine. Or you could come up with a decimal if you use your calculator. I'll accept any answer. We found the magnitude of E total. It's that number. That's sufficient for your answer. I wanted the direction, which you could draw with a vector. You could draw a good idea of what the direction is. And the magnitude, which we determined from vector addition. If I were to break this up into horizontal and vertical components, it would be a few extra steps. What I would do is create a triangle here, a right triangle. Whenever you have a right triangle, you can use sines and cosines to figure everything out. This is even a special case where I know what this angle is, 45, this angle is 45, so it's a 45, 45, 90. Because of that, I can very easily figure out if I know what EC is, you know what EC is, figure out what these components are. And then I could break this up also into vertical and horizontal components. Again, it's a 45, 45, 90 triangle, and so it's pretty easy to find out what these components are. Once you have only horizontal and vertical components, you're going to end up with, we'll end up with something that starts here, goes a little to the left because this is smaller than this. So I do this, subtract this, and find out I get a vector in that direction. Then we get a vector that goes way up. It's the addition of this plus this. And our final vector would start at the way beginning and go to the way end. It'd be our same E total that we already determined. The reason I would want to break it up is because maybe I didn't have a 90-degree angle there and I needed to figure out how to add these vectors together. And we can add vectors together easily if we come up with a right triangle. And so if you come up with horizontal and vertical components, you'll end up with some sort of right triangle. And you can easily solve for the hypotenuse of that. Okay, let's go on to this last question. I have two charges. This was a little different for both classes, but it was the same idea. E and F. Let's say E is a positive 4 coulomb charge, and F is a positive 3 coulomb charge. I asked, where is the electric field 0? So again, these are two positive charges. Yes, they repel each other. I don't care. I'm not asking for that. I'm saying, where is the electric field 0? That means we're pretending that these are nailed down for just a moment in time, and we want to know if there's a point where the electric field is 0. Well, there are kind of three ideas. It's got to be linear. In other words, if I was choosing a point up here, my electric fields would point in different directions. And if my electric fields point in different directions, they'll never cancel each other out. So it can never be 0. And so the point where the electric field is 0 must lie along this line, because along this line, it is possible that I'll get these two electric field vectors, one due to E and one due to F. If I get a point where they're the same magnitude and opposite directions, they'll cancel each other out. So the point of interest is either going to be somewhere to the right of both charges, somewhere in between both of the charges, or somewhere to the left. If I choose a point to the right of both charges, both of my charges are positive. That means the electric field always points away from them. The electric field due to F would point in this direction. The electric field due to E would also point in that direction. So if I choose a point to the right, they're never going to cancel each other out because the electric fields add together, they work together in the same direction. Similarly, if I choose a point to the left, the electric field due to E points away from E. The electric field due to F points away from F. And since these electric fields are in the same direction, they're never going to cancel each other out. What about if I chose a point in between them? The electric field at this point, due to E, will be to the right. Let's look at right in between them. It'll be to the right, and it'll be due to a 4 coulomb charge. So this vector is going to be longer than this one. The electric field, this is due to E. The electric field due to F will point to the left because it's pointing away from a positive charge. it'll be a little weaker than this one. That is, the magnitude or the length of the vector will be less than this one because it's a smaller charge. But I can see that portions of these electric fields cancel out. They're pointing in opposite directions. And so I suspect if I move my point away from the center, I can find a location where the electric field will be zero. In fact, I want to move a little further away from this charge. Since it's a bigger charge, if I move further away, I can make the electric field due to that charge weaker. So let's move over here. There's some point over here where there's an electric field due to E in that direction, an electric field due to F in that direction that are the same magnitude, and they'll cancel each other out. I know they could be the same magnitude somewhere over here because even though the electric field due to this is stronger because it's a bigger charge, I made it weaker because I'm further away. Even though the electric field due to this is weaker because it's a weaker charge, I made it stronger by getting closer to it. And so I'm looking for a balance where the strength of the electric field due to each charge can be the same. And the balance must be where I'm further away from the bigger charge and closer to the smaller charge. Let's come up with an equation that can solve for this exact location. First of all, I need to show you, or I need to write a variable to describe my location. I'm going to describe it by a distance x. Let's say we're some distance x, which tells how far away I am from F. You have to actually draw this in order to complete your answer. If you give me a value x equals something, I have to know what does x refer to. I also tell you that the total distance between these two charges is 1 meter. And so even though I have some distance x, or whatever I want to call it right here, L, this is actually equal to 1 minus x. That is, if I have some distance x here, then this distance must be 1 minus x, because I know that this plus this is equal to 1. In other words, if I did call this L, I would say x plus L equals 1. And I could solve for L in terms of x. L is equal to 1 minus x. Now, do I have enough information to write out these E fields? I have my constant, Coulomb's constant, Q, which are these charges, and the distance R. Now I've represented the distance R from each charge in terms of one variable, x. That means if I write out this equation, there will be just one variable to solve for, and hopefully we'll be successful. So I'm looking for a point when the electric field due to E is equal in magnitude to the electric field due to F. There may be some point out here where I get the same answer, where they're equal in magnitude, but for this specific case, they're also pointing in the opposite directions. And so I want to find a value where x is positive, where x is towards, in between. The x position is in between my F and E charge. Let's write out these equations. E due to E equals E due to F. This is k sub E times Q due to E is 4 over my distance to E is 1 minus x, and I have to square it. This is my electric field due to charge E. My electric field due to charge F, again, is k sub E times 3 over, and my distance is x squared. Okay, now we can come up with our quadratic equation. We could just cancel out these k sub e's. That is, we're dividing both sides by k sub e. Let's multiply both sides by 1 minus x squared and multiply both sides by x squared. So we end up with an equation 4x squared equals 3 times 1 minus x squared. Sorry, 1 minus x squared. Don't want to make that mistake. Now we can multiply out this, whatever's in the parentheses. 1 minus x squared is 1 minus x times 1 minus x. I do the first, outer, inner, and then the last. So 1, multiply these two together, minus x, then minus x plus x squared equals, I'm just going to put it like this. So my equation is, let me draw it over here. 4x squared equals 3 times x squared minus 2x plus 1. I want to bring everything over to the same side. Let me first multiply this 3 out on that side. And now let me subtract each of these terms individually, so everything's on the left. That's x squared, because 4 minus 3 is 1, plus 6x minus 3 equals 0. So now we have some quadratic equation. It's not a perfect square, so I can't solve for it in my head. I'd have to go find some quadratic equation solver, use my calculator. You could even plot this equal to y and find out where does it cross 0. And that's the correct value of x that we're looking for. Of course, we want a value of x that makes sense. It'll be a value less than 1 because it'll represent a position between this point and this point. And we want a value that's positive to show it's in this direction from f. You can plug it in and solve for it. This was enough of an answer that I was looking for, just the equation that we needed to solve for. We know the general location will be to the right of center for this scenario. We know the equation we need to solve for is that.